An object near the surface of the Earth is accelerated by gravity. The gravitational acceleration g is equal to the gravitational force divided by the mass of the object and is felt everywhere. This can be referred to as a gravitational field, which is produced by Earth's mass. Since gravity has a magnitude and a direction, it is a vector, and thus the gravitational field is a vector field. This suggests that the Earth produces a kind of disturbance in the space around itself that affects other objects in the field. In the same way, a charged object sets up a disturbance in the space around itself. This is known as an electric field. The electric field is usually designated capital E. Like gravity, it is a vector field, since it has both magnitude and direction. Like the gravitational field, the electric field is associated with a force. In this case, the electric field is equal to the electric force divided by the value of a test charge Q0 placed in the field. If the test charge is released and both charges are positive, the test charge will move away under the influence of the electric force consistent with the concept that like charges repel each other. A positive charge exerts an electric field that points away from the charge. A negative charge, on the other hand, exerts an electric field that points towards itself. Thus, if the positive test charge is placed in the field of a negative charge and released, it will move towards the negative charge. This is consistent with the idea that opposite charges attract. The electric field exerted by a charged object can be calculated quantitatively. Suppose a sphere with charge Q is present and a test charge Q0 is placed nearby. The electric field exerted by the central charge on the test charge is equal to the electrical force divided by Q0. Now use Coulomb's law for the electric force that relates the value of the charges and the separation distance between the charges. Notice that the final expression for the electric field created by the charge Q is independent of the test charge Q0. This is because the electric field generated by a charged object is present regardless of whether another charged object is nearby or not. The concept of field lines was developed to provide a means for visualizing fields, including electric fields. At all locations in an electric field of a charged sphere, the field is directed radially outward from the sphere. An electric field diagram can be created by drawing lines extending outward in all directions from the sphere's center. For a positive charge, the electric field lines point away from the charge. If the charge is negative, the electric field lines point towards the charge. If more than one charge is present, the total electric field is equal to the sum of the electric fields of the individual charges. This can lead to complicated electric field line configurations. For example, here are the electric field lines for two equal positive charges. Notice that at a point in between the two charges, the electric field goes to zero, and at that point there are no field lines. If one of the charges is positive and one is negative, the field line configuration gives an indication of the attraction between the two opposite charges. There are two basic rules to consider about electric field lines. The first is that the density of field lines indicates the field strength. For example, here it can be seen that near both charges, the field lines are very close together. With increasing distance from the charges, the field lines spread, indicating the electric field is getting weaker. The second rule about electric field lines is that they point away from positive charges and towards negative charges. This can be seen here by the direction of the arrowheads. Let's now calculate the value of the electric field for different types of configurations. First, consider equal positive and negative charges separated vertically as shown. What is the value of the electric field at a horizontal distance r from the charge, if the distance from the horizontal line to each charge is a, as shown in the diagram? Qualitatively, which diagram best represents the electric field resulting from each charge? Incorrect. The electric field. Incorrect. Correct. The total electric field at point P is given by which expression and its associated diagram? Correct. Because the charges are equal in magnitude and the point P is along a line that is the perpendicular bisector of the line separating the charges, which natural symmetry can be exploited? Correct. For the angle theta shown, what is the vertical component of the total electric field? Correct. What is the magnitude of the electric field due to each charge? Incorrect. Incorrect. Correct. What is the total electric field? Incorrect. Make sure. Correct. How can the cosine be expressed in terms of r and a? Correct. We now have an expression for the total electric field. If we make one last assumption that the charge separation, distance a, is much smaller than the distance r, what does the total electric field simplify to? Incorrect. Check your... Incorrect. Correct. This is known as the electric field due to a dipole. Notice that along the horizontal line shown, the electric field for a dipole falls off as 1 over r cubed, rather than 1 over r squared, as for a single charge. A dipole configuration is set up when equal and opposite charges are close together. The field lines for a dipole can be seen here. How does a charged particle behave in a uniform electric field? Let's take a look at the case when we have two long charged plates that have equal and opposite charges. Between the two charged plates, assuming they are long and you can ignore effects near the edge, the electric field is uniform. From our two rules governing electric field lines, the equal spacing of the lines indicates the uniform nature of the field, and the arrow of the field lines points from positive to negative. If the test charge is positive and is released from rest, which direction will it move? Correct. The positive test charge moves toward the negative charge. To determine the motion of the test charge, we can use Newton's second law. Note that by exploiting the up-down symmetry of the problem, you can reduce the problem to one dimension, and you need only deal with a scalar equation. What is the force acting on the test charge? Correct. Putting this into Newton's second law, you can solve for the acceleration. Since the electric field is uniform, what statement can be made about the acceleration? Correct. Since the acceleration is constant, the kinematics equations can be used to define the position with time and the velocity with position. You probably recall that these motion equations are very similar to that found for an object in free fall. Thus, when released, the charge falls towards the negative plate. Parallel charged plates are used to deflect charged particles that move through the plates. If a negatively charged electron enters the region where the plates are located, it is accelerated by the electric field, and its path is diverted. When the electron emerges from the plates, it follows a straight line since it is no longer being accelerated. If the electron hits a fluorescent screen placed at a location beyond the plates, a small bright spot is formed. This is the basic principle of how a cathode ray oscilloscope, and ultimately a TV, works.